So in the previous example, when we were looking at nails, we used dozen to give us a number. In chemistry, we're going to use a number that's known as a mole. And it's similar in many ways to a dozen in that it is a word that signifies a number. However, this number is so huge that it's really beyond our everyday usage, probably even beyond our comprehension. A mole is equal to 6.022 times 10 to the 23, which is an absolutely huge number. Here's a mole written out in standard form. Right here's a million, a billion, a trillion, quadrillion, quintillion, 602 sextillion. That's what a mole is. This is huge, beyond any number that we could actually count to in our lifetime or use in our everyday life. However, atoms and molecules and ions are so incredibly small that this number, large as it is actually useful. So a mole always is this number, 6.022 times 10 to the 23. Just like a dozen is always 12. So if we think of a dozen donuts, always 12. A dozen bagels, always 12. A dozen nails, always 12. A dozen eggs, always 12. Same thing with a mole. A mole is 6.02 times 10 to the 23 things. However, in chemistry, the things that we're going to be talking about are typically atoms, ions, or molecules. This is also known as Avogadro's number. Avogadro was an Italian scientist. He did not come up with this number, but it's named in honor of him. So how did we come up with this number? Well, like all standards, all measurements, there has to be some kind of standard. So this was based on the standard of how many carbon atoms are in 12 grams. And by carbon atoms, I mean specifically the C12 isotope, which means there are 6 neutrons, 6 protons, and 6 electrons. So this is a definition. One atom of carbon-12 weighs exactly 12 AMU, and all other atoms have their mass based on this standard. We also use the standard to define a mole. We took 12 grams, we meaning scientists, not me, 12 grams of carbon, C12, this isotope only, and figured out how many atoms were in it. In 12 grams, exactly 12 grams of C12, there are 6.022 times 10 to the 23 atoms. So this is how we got this number, but this number works for anything. For example, if we have 6.022 times 10 to the 23 atoms of sodium, then we have 1 mole of sodium. If I have 6.022 times 10 to the 23 atoms of iron, then I have 1 mole of iron. Just like if I have 12, I have a dozen. If I have this number, I have a mole. And here are the ratio configurations of our conversion factor. We're going to be using this relationship, that this number means a mole, in doing our railroad math. And so this is what it's going to look like in one of our railroad compartments, either like this or like this. And which number goes in the denominator depends on which we're trying to cancel out. So let's look at an example of how we're going to actually use this conversion. A silver ring, and a silver ring contains 1.1 times 10 to the 22 silver atoms. How many moles of silver are in the ring? Okay, so let's start out with what we're given. We're given 1.1 times 10 to the 22 silver atoms. So this is an actual number. This is how many silver atoms there are. And what we want are moles of silver. So anytime we need to convert between moles and atoms, the conversion factor is always Avogadro's number. 1 mole of anything. So 1 mole of silver atoms is equal to 6.022 times 10 to the 23. So if we look at our unit check, here we have silver atoms, and these are the pure numbers here. These are just numbers. We're not measuring like we are with pounds or length. And then here's mole, 2 moles. Mole is going to be a unit for us, just like dozen was a unit for us in our previous example. So now that we have 2 of everything, 2 silver atoms, 2 moles of silver atoms, and let me just put up atoms here to be consistent. Let's go ahead and do our railroad math. We start out with what we're given, which is the 1.1 times 10 to the 22 silver atoms. And since I have silver atoms here, I have to have silver atoms on the bottom. So 6.022 times 10 to the 23 silver atoms. And then the other half, 1 mole of silver, goes on top. Now my silver atoms cancel out, and I'm left with moles of silver atom, which is what I want. And now I let my calculator do the work. 1.1 times 10 to the 22 divided by 6.022 times 10 to the 23. And before I go any further, I'm going to say what my answer should be. It should be less than 1, because this is less than a mole. A mole is 6.022 times 10 to the 23rd, and this is 1.1 times 10 to the 22nd. So I should have less than a mole when I get my answer. Okay, so my calculator gives me this, and that's going to be moles of silver. And when we're talking about atoms, because silver exists as atoms, we really don't need to put the atoms here. But it doesn't hurt. I'm going to write it here just for clarity. And if your calculator puts it in scientific notation, this is probably what it looks like. Now let's look at significant figures. We have 2 sig figs in our given value, so our answer should only have 2 sig figs. Here's my last allowable significant digit. I'll look to the right, that's less than 5. So I'm going to cut it off there, and same thing here. It's a lot easier to round when it's in scientific notation, because you don't have to worry about any leading zeros. So the final answer, expressed in correct sig figs, is 1.8 times 10 to the minus 2 moles of silver atoms, or 0.018 moles of silver atoms. Both these values are equivalent, and unless I specify, let me just separate those out, unless I specify that I want it in scientific notation, it doesn't have to be. But it is really a lot easier to round if something's already in scientific notation, because as I said, you don't need to worry about those leading zeros. Now you should check in your calculator that you get the same answer, because we're going to be using these exponent keys a lot. Now pause the slide and see if you get, or see if you can work out this problem. Calculate the number of atoms in 2.45 moles of copper. Okay, let's see how you did. The first thing you want to do, the first thing that you want to do is you want to write down your given value. We're given 2.45 moles of copper, and we want number of copper atoms. Now copper as a metal, and here it is as an element, is made up only of atoms. So we don't specify here that copper is made up of atoms. Chemists know that. But if it helps you, you can write copper atoms here. So if we have 2.45 moles of copper, we have 2.45 moles of copper atoms. And we want to know how many copper atoms there are. Well, there's just one conversion factor that takes us between mole and number. And here it is. 1 mole of whatever we're looking at is equal to 6.022 times 10 to the 23. And in this case, we're looking at copper atoms. So now I have moles here. So down here I also have to have mole. So 1 mole of copper, and the other half of my conversion factor goes on top. Okay, so my calculator, see I'm running out of room here, let me write it down here, tells me 1.47539 times 10 to 24th copper atoms. And my moles canceled out, and the units I'm left with are copper atoms. Okay, so let's go back and look at sig figs. My original value has 3 sig figs, so 1, 2, 3. This is a 5, so 1.48 times 10 to the 24 copper atoms. Okay, now let's see. Does this answer make sense? Well, I have about 2.5 moles of copper, and every mole is 6.022 times 10 to the 23. So this is more than 6.022 times 10 to the 23, but not incredibly more, just an order of magnitude. So yes, this answer makes sense.